welcome to everybody. Today we talk about we start to get into the core of the course. It's about floating-based robots, legged robots. And to talk about legged robots, first we need to talk about floating-based robots. The legged robots are it's a broader class of to whom the legged robots belong. So first, why do we care about floating-based robots? Well, industrial manipulators we saw till now, they are fixed-based robots, and they are fast and accurate in some specific tasks, and they work well in known structure and static environments, workspaces. But whenever we go outside in the real world, the robot must be able to freely move, interact with humans, and first of all move in unstructured, uncertain, and dynamically changing environments. And for this, we need some robots that are able to move around, that are mobile robots. And possible applications are, for example, exploration of collapsed houses, nuclear plants, mines, inspection of oil platform ducts, cluttered environment where humans cannot go, and search and rescue. As we said, we might have an earthquake, and in the recovery phase after the earthquake, most of the houses can be damaged and can be collapsing. So sending a robot to acquire a map of the environment instead of sending like a firefighter person, a human, can be beneficial, because if the house collapses, we lose the robot and not the human. Transportation is a new application that is interesting, because the robot can be a collaborative element in the work, where bringing like to the workers materials and different stuff that they need, without having the human self going to pick it up from the warehouse. As I said, the mining also is an application for the commissioning, especially now that we are going to green energy and we are moving out from the nuclear. There are some old plants that need to be dismantled. Also for monitoring, patrolling, surveillance of some areas. And finally, in the agriculture field, the legged robot is, thanks to the legs, it's not so invasive in the modifying the terrain where it works. So it's not, for example, in cases where we want to selectively put herbicides to plants without destroying with trucks the terrain around, a legged robot it's an ideal solution. We have some examples. Mobile robots are also used in underwater applications, in space applications where we need to, for example, collect a satellite piece from the International Space Station, or there are also drones that nowadays they are starting to be used as for deliveries of goods, and the mobile robots with wheels for monitoring, for cleaning, trucks for the mining, they are mainly used, and finally legs. So we saw here two examples for transportation and this platform for research. So first, what is the most important characteristic of a floating-based robot? Is that the base, its base is not fixed but is a moving body, and in general is under-actuated. So a fully actuated robot has a number of actuators equal to the number of degrees of freedom, at least, while an under-actuated robot has a number of actuators smaller than the number of degrees of freedom. And in the case of an under-actuated robot, the base can be controlled in only one way, through the action of external forces that can be, for example, contact forces, or if you have a space robot, rockets, propulsors. So this is the situation where the robot, for example, is floating in space and can control dispose the pose of the space through the action of rockets. In the case of quadrotor, the rockets are fans, are propellers with electric motors that creates airflow that stabilize the base of the drone. And in the case of a legged robot, we have the contact forces that drive around the base. So now we will talk about legged robots. And legged robots are a peculiar class of floating base robot with single chain kinematic structures. So we think about a floating base link that, for example, is a trunk, and then from there they start to branch out kinematic serial kinematic chains that are the legs and the arms, the limbs. Let's say if you have an hexapod, you have 6. If you have a quadruped, you have 4. If you have a humanoid, you have 4. So there are no kinematic loops. There is no such thing like a Stewart platform or some closed kinematic chains. And differently from a fixed base robot, legged robots can fall because the base is under-actuated. So the whole problem of legged locomotion boils out into the problem of creating the right contact forces on the ground to keep balance, counteract gravity, and move in the desired direction. So I'll give you here a brief history on legged robots. The legged robots start to be the first ones to be designed and presented to the world back in the 60s with the General Electric walkie truck. This is an hydraulic machine, huge, operated by a human. It was moving statically stable but was walking already. Then came out in the 72 the ZLT concept. We talk in the second part of the course extensively. The first humanoid robot from Zeta University, 1973. Rybert was in the 70s, 80s, was designing the first jumping robot with an onboard. I'm not sure if the computer was on board, but it was a seminal work for the whole robotic community that works on legged robots, because he was able already back in the 80s to make jumping robots and doing somersaults. Then there was a branch of works on starting from the work of McGear on purely passive dynamics robots. So these robots are just walking down a slope and having a smart configuration of the masses of the link, such that you can establish a linked cycle walk. But it is cool from the principal point of view, but it's of limited practical application. Then with Honda, we start to have the first humanoids with onboard batteries, walking on flat floor, and then you see here the operating scale, because more and more stuff is happening in the latest year. We have Asimo, the first humanoid was also able to jump on the place, and HRB RP2, which is extensively used in the research lab on leg robots, and finally in 2008 the Boston Dynamics Big Dog that everybody knows. It's an hydraulic quadruped, and it was able to walk on rough terrain. So start to go out of the lab in slopes, in the forests, and in different terrains. Then in 2010, this is IQ, our first prototype we designed as well. It's an hydraulic robot with 12 degrees of freedom. ICAB, the humanoid of the child humanoid of IIT. And then we have DLR designing Toro, which is the first torque-controlled humanoid, at least apart from Atlas, which is from Boston Dynamics. Animal from ETH Zurich, as well a quadruped robot that is electrically powered with electric actuators, and Walkman IIT humanoids, big humanoids, as well electrically powered, and finally Atlas, that is hydraulically equipped robot of Boston Dynamics that was even able to do a somersault and do very crazy motions on every terrain. And the peculiarity of this robot is that they reduced the mass a lot to around 60, 70 kilograms, and this was a key feature to achieve such performances. They have a brilliant, big team of engineers that carefully design the best actuator solutions and the best sensor solutions. So they're able really to cut the limits, to do cutting-edge technology and reach the limits of what is possible, but they don't publish. So everything is secret. Nobody knows anything about them, their work. And finally, our last board from our lab, IQ from IIT, it's the evolution of IQ, and has a peculiarity to be completely power autonomous, untethered. There is no harness, safety harness, and it's operated, and is able to. It was showing off to pulling a plane as capability of the hydraulic actuators that are useful for heavy-duty applications because of the power density. So in a small actuator we can have a lot of power. Then why humanoids with respect to quadrupeds? First, well, the idea is to using humanoids is their adaptability to human environments. So we need to think that humanoids can be more easily work in environments that are structured for humans, and use machine design for humans, and also the psychological and commercial reasons. So having a quadruped is less comfortable maybe to work with than some robot that looks like a human. While the quadruped, instead, their advantage is their higher stability, because they have a larger support polygon area. They have smaller feet, most of them. This is due to simplify the kinematics, because we don't to position a point in the 3D, we need 3 degrees of freedom, and the ankle joint, it's an additional complexity. We already have 4 legs for the stability, so we don't. A humanoid with point feet, it's inherently unstable, while a quadruped with point feet can be perfectly stable. So that's why humanoids have the ankle joint and they have a flat feet. They can perform different kind of gaits. For example, walk, which is moving the diagonal legs in synchronous. Trot, walk, which is moving one leg at a time. Trot, which is moving the diagonal leg in synchronous. And pace, which is like what the camera does, moving the lateral legs. Let me see. As sensor equipment, we have several kinds of sensors that can be grouped into two big groups: the proprioceptive sensors that are measuring some quantities of the joints of the robot itself, and there are, for example, encoders that are we talk about them, and they're measuring the position, digital encoders, joint sensors. That can be, I don't know, load cell for linear forces, or a torque sensor specifically designed to measure the torques. In IIT, we have a long experience in designing this kind of sensor, also 6-axis, but one axis. They are quite tricky because if you don't design properly, you might have residual stresses that are creating hysteresis. So one way that we found out was very successful into designing torque sensors is to use mechanical locks to transfer the effort. So this sensor, they are assembled with some mechanical keys, and there are no screws to keep them together. Because if you put the screws, the micro slippage, even if you tighten the screw very much, this creates an hysteresis. It creates a local deformation in the strain gauge, and then whenever you change the motion, the micro slippage, it creates an hysteresis in the torque measurement. And it took a lot of time into understanding this. Then you have some sensors to measure the orientation of the base, of the floating base, and the velocity and acceleration. And this is called IMU, which is Inertial Measurement Unit. It is a very small package. This one costs around 2,000–3,000 euro. There are more expensive ones that are practical grade IMU that can go up to 40,000 euro, and they have less drift. So the much it costs, the less drift you have, the more accurate the measurement. And this IMU, as for example, a magnetometer that is not accurate at all, because it's very sensitive to the noise, electrical noise in the environment. So don't trust if you measure the yaw, the heading, because you use the magnetometer to measure the heading of the robot. Don't trust in this measurement too much. I would rather use odometry to estimate the yaw. Then here's an internal camera filter to give you roll pitch angle as well, given an inclinometer, because it senses the direction of the gravity vector and discard it from the acceleration part. And then as an accelerometer, 3D accelerometer, and a gyroscope, so we can measure the angular velocity and the linear accelerations, and also the angular acceleration. Then, so this is what we use, and we will use in the last lecture to close the loop on the orientation of the trunk. So whenever we do the whole body control that controls the trunk orientation, we close the loop on the output of these sensors. Then we have exteroceptive sensors that are sensors that allow the robot to perceive, to give a perception of the environment surrounding himself, like obstacle, people, terrain, shape, and they are mainly divided in infrared cameras, RGBD. They are called cameras that have these infrared sensors, and stereo cameras. So in this case, the infrared gives you the distance of the point that is perceived and is located in the RGB map. And stereo cameras is that they get the three-dimensionality of the map using merging the images from two cameras. Of course, this is very dependent on the illumination of the environment, so they are quite tricky. And laser cameras is a similar idea of the infrared sensor, but it's a laser that it's a blade of laser emitters that rotates around and gives and gets the position of all the points. The density of this one is much better. This is due to the cost, it's more sparse, the kind of map you can get, but this can get up to 180 meters, 100 meters. This one has not such a range, so you normally use both of them. This is for the broad level navigation, and this is for short-term navigation. So to decide where to put the foothold, you need a local map that is built with this sensor, while to navigate, let's say, in a big environment, you use the coarse map, use the acquired with the line. Of course, you can fuse both and achieve a better map. So I will give you some basic terminology we use here in the Leg robotics community, and one is the support polygon. Support polygon is considered the convex hull of the contact points. So it means that if you have a humanoid walking and the humanoid is standing on one foot only, the convex hull, the support polygon, it's the area of the foot itself, and whenever it starts to touch down and goes into a double stance situation, the support polygon becomes the convex hull of the 2 feet. And we will see that the support polygon is very important for stability. For quadrupeds, instead, the thing is a bit more complex. So in humanoids, the support polygon either is like this or like this. In quadrupeds, it really depends on the kind of gate you have. So in quadrupeds, we define a gate with a gate scheduler. That is a diagram that tells which leg should be swinging, and it should be in swing or in stance at each moment of time of the gate cycle. So normally the gate cycle is parameterized between 0 and 1, and you have a percentage of that. Let's say, for example, here the left hind leg is swinging, then here is in stance, then we swing the left front, then we swing the right front, and then finally we swing the right hind. And then we cycle again, so we repeat endlessly this cycle. And this is the crawl or the walk example. In this case, the support polygon will be changing according to the legs that are in stance. We have a situation in which we have 4 legs in stance. So let's say we want to move the central mass we want to move this leg, we want to move the central mass in this triangle to be statically stable. Then whenever we swing the legs, the support polygon becomes the convex hull of the legs in stance that are these 3, and then whenever there is a touchdown, the support polygon becomes again a quadrilateral with a different shape. In case of a trot, what is the support polygon looks like? How does it look like? In the trot you move diagonal legs, so you have 2 legs, it's a line, yes. And in the case of a pace, like a camel, you move the lateral legs, it's also a line. Then there is another gate, which is not the gallop but the bounding. The bounding is it's a gate that I don't know, antelope does, and is in essence having these 2 legs, ballistic phase, these 2 legs touching, then again these 2 legs. In this case as well is the line connecting the front legs or the back legs. So a bounding is something like this. Then the central mass we will use extensively for the computation. In the case of a legged robot or a quadruped, it's the same. We need to consider the central masses of all the links and do a weighted average of their location of these masses with their locations divided by the total mass of the robot. So these are xi are the position of the central masses of the links I in the frame of interest. Of course, this need to be done. They need to be mapped in a common frame that normally is the base frame, is the frame of the trunk. Do you have any question? Cool. Let's go. To the modeling part. So now that we know what a legged robot, or more general a floating based robot is, how do we model it? There are different ways to model, and the most intuitive one, let's say, it's the minimal coordinate one. Then we go through another one that is, in my opinion, more sound for most compact possibilities, especially for quadrupeds, which is excess of coordinates. And then we analyze the structure of the floating base dynamics. So the minimal coordinate is the most intuitive because you consider the floating base robot as a fixed base robot, setting the root of the root frame of the robot at the contact point. So in case you have two contact points, you need to decide one, and then you consider like the robot as a serial chain branching out from that contact point. So for each contact configuration, we will have a different set of joint variables, each one with a specific kinematic structure and dynamic model. Instead, in the case of excess of coordinates, we have always the same kinematic structure, but we have a floating base system, a floating base. We model the location, the pose, the position orientation of the floating base link, and then we allow the possibility to add or remove contacts whenever they are happening. And we'll see afterwards how to model this floating base link pose. So in the minimal coordinate, the idea is to get the minimum amount of coordinate for each contact mode. Let's think, for example, you are in a stance, single stance configuration of a humanoid, and in this case, how many degrees of freedom I need to describe the configuration of the robot. Let's say we put the fixed base here.
So the number of operators that yes.
In this case, specific.
Plus the other.
Okay, yeah, that was an error in my slide. I wanted to see. So there are three, which is the location of the first link with respect to the root frame, to the fixed base, which is located here. Plus you have the knee, the inclination of this link. This is called theta knee, and then the inclination of the trunk. Then you have also the other two. So you have 5. I put only 3 because I considered one length, but it was wrong. In case the robot is flying, in this case we need to define the location of the trunk, and then also having the other 5 link. So in this case you have we are talking about the plane, so we have the position, the trunk of the time frame in Z and X coordinates. Then you have the location of the torso here, which is theta torso, and theta hip, the location of the height of the robot, and then the lower leg is theta knee, and then you have the other two of the other leg. So in total you say 7 if you consider both legs. So 5 to 7 degrees of freedom. Then the good thing of this approach is that you have less degrees of freedom as possible according to the situation. So this and variable is changing all the time, but it's the minimum one. But if you, whenever you put a foot on the ground, you use either 6, depending on the type of contact, degrees of freedom or 3, and you need a different set of joint coordinates, generalized coordinates, to define the robot configuration. So if you think about a humanoid, you have 4 contact modes. One is whenever the stance, the right leg, for example, the A leg is tense. The other one is whenever you have the left leg, the B is tense. And then you have the situation we saw before, the robot flying, or the situation where the 2 legs are on the ground, it is a double support phase. And so we have 4 modes, and if you consider the whole possible transition between these 4 modes, you have 12 possibilities, and so for each possibility, you need to consider you need to change the mode. So you need to have this transition. While if you have quadrupeds, you have 16 modes, so you can imagine the amount of transition that you need. So this is not tractable at all, the quadrupeds with minimal coordinates. We need to go resort to another approach that is called excess of coordinates. So in the excess of coordinate approach, the joint angles are not enough. We need to describe the robot configuration because we have also the floating base. And the idea is to add a virtual kinematic chain of 6 degrees of freedom between an inertial frame that is attached to the lab, to the board, and the base frame, the floating base frame B. And then describe the robot configuration as this floating base pose, position orientation, and the values of the joint angles. This is QB, where we said that QB is the configuration of the floating base with respect to the board. So this is the base frame, this is the board frame. And each link, the pose of each link can be retrieved from the pose of the base frame and the joint configuration. So if we know the pose of the base frame, we can work out for kinematics, given the joint angles, the position of each point in the robot. Okay. Everything's clear? But to describe the pose of the floating base, we know that we can have different representation that depends on how we parameterize the orientation representation of the pose of the floating base. So let's say we can have different kind of generalized velocities. One approach is to use virtual joints that are 6 virtual joints that are 3 prismatic joints and 3 rotational joints. The 3 prismatic joints that represent the position of the floating base, while the 3 rotational joints series are representing the orientation. And because there are subsequent rotations, these 3 rotational joints are represented by Euler angles, while the free prismatic joints is represented by a vector, 3D vector of the position of the base. So the base pose configuration vector is 6-dimensional. We have a 3D vector of position, Cartesian position of the base, and a 3D vector of the orientation of the floating base represented through Euler angles. The velocity of the twist, that's called the generalized velocity of the floating base is the derivative of this vector. We have velocity of the center of the base and the Euler rates. And if we compute the Jacobian, for example, that maps to the spatial velocity of the floating base, so velocity, linear velocity, and angular velocity of the base, we need we know that we need the mapping because our QB it's a different vector. So the mapping is this, and it's a Jacobian that has the identity in the linear part and the mapping, the nonlinear mapping that maps Euler rates into omega in the angular part. And we know that this linear mapping is orientation dependent. So the good thing of this approach is that we have a direct relation between the ripple chain kinematics and the generalized velocity, because one is the derivative of the other. But and they are also easy to, for this reason, to numerically be integrated, because you can get QB dot and just do a simple order integration, for example, and get the QB. However, we know that we have singularity associated with the Euler angles. This is a disadvantage of this approach. We know that you have a gimbal lock singularity problem when the roll and yaw axis are aligned, and so whenever we have 90-degree pitch. So there is another approach that we call the free floating body approach, which we consider as the generalized velocity, the spatial velocity of the floating base. So the velocity of the linear velocity of the base and angular velocity. But how do we represent the configuration part in this case? Depends on the parameterization that we choose. In this case, the Jacobian of the base, JB, is the identity, because we have, in essence, the spatial velocity of the base is equal to the QB dot. If we choose for the orientation the quaternion as a parameterization of the orientation, we are sure that we have no singularities because it's a non-minimal representation, but we have 4 elements to represent the orientation. So the poles and the velocity of the base, they don't have the same size. In particular, the pose has 7 numbers to be represented, 3 from the position and 4 from the quaternion, and the velocity has 6 numbers for linear velocity and angular velocity. And this way, it's wrong to say that we can integrate QB dot to obtain QB. So the integration we need to integrate the quaternion and do convert it to angle axis as we saw. If we use, to summarize, if we use the quaternions to represent the orientation, the robot configuration becomes, the total robot configuration becomes n plus 7 dimensional. because the pose is 7-dimensional, then the robot velocity is n plus 6-dimensional. And when we write q dot, we have a slightly different notation because the dimension of q, as we say, is different from the dimension of q dot, so it's not good. We should change notation. We don't do this in this course for simplicity, but remind that this is just not the good way to write. And the robot acceleration as well. This time is there same dimension, so it's correct to say q dot is the derivative of q dot, and it's n plus 6-dimensional. And in this case, we have the acceleration of the base and the angular acceleration of the base. So if we now write the dynamics for this floating base robot, how does it look like? The same as in the fixed base robot. This time q dot will not be n, will be n plus 6, and all the vectors will be, so there will be n plus 6 equations. The torques, however, because the floating base is underactuated, we are not applying torques to the floating base, so we will have a selection matrix ST that tells us that we have torques only at the joints, equators. So the torque factor is n-dimensional, and then we have the contact forces that back into the floating base equation dynamics with the Jacobian. Plus, we have the contact constraints, the holonomic contact constraints that tell us that the foot velocity should be 0, and also the foot acceleration should be 0. Nothing changes. It's very elegant, this approach. And with the matrix form, this is the equation of the dynamics, wherever we have acceleration of the joint, contact forces, and this is the constraint that the feet are in contact, and the dynamics, the floating base dynamics. So if you want to solve this in a simulator, you can use this equation and work out the values of this. In summary, with minimal coordinates, we have different number of degrees of freedom in each contact mode. We see that floating base has a bigger number, and the standard space we have a smaller number, and you need to take care of the transition between the contact modes, and also we know that this approach naturally embeds the contact constraints in the choice of coordinates, so you don't have to care about adding the contact constraints as in the excess of coordinate situation, and is suitable for systems with very simple contact scenarios, like one contact, maximum 2 contacts. One in the excess of coordinates is more generic. You can have as many contacts as you want. You have always the same number of degrees of freedom, so you use only one coordinate convention or one set of generalized coordinates. You can simplify the code this way. You have a different you deal with a different number of constraints, as you know, through the Jacobian matrix that will change dimension according to how many contacts you have, and adding this to the appending this to the dynamic equation. Everything is clear? Okay. Let's have a look now to the structure of some particular structure of floating base dynamics that allows us to simplify the trajectory planning task if we exploit it. In particular, if we can differentiate already in the structure of the dynamics, if we write it extensively, the previous equation, we can underline that the fact that we can partition the actuated dynamics, which is the n-dimensional, the last n equation of the floating base dynamics, from the underactuated dynamics, that is the first 6 equations of the floating base dynamics. And we can see that there is no way, as we said, to move the floating base apart from the usage of the contact forces, apart from some coupling coming from the joints. Let's say the most effective way to move the base acceleration is to use the contact forces, because we have an underactuated base. So these contact forces in general are expressed, are acting in a frame C with the origin in the contact, and usually for simplicity is aligned with the bore frame. So we usually we can write this equation in either frame. We can, for simplicity, think about writing this in the bore frame, and then the Jacobian of the contact maps the robot velocity into the generalized velocity of the robot into a twist at the contact, or the Jacobian transpose maps back the forces into torques. So if we look at like to the contact Jacobian, depending on the kind of contact, the contact Jacobian maps into either a linear velocity of the foot, or in the case of a full flat foot and 60 contact, we have also the angular velocity of the contact frame. And in general, because of the floating base, now we don't have anymore, no longer have an n degrees of freedom robot as a fixed base case, but we have an n+6 degrees of freedom. So we have the Jacobian partition in 2 parts. One is we call JCD, which is the effect on the foot velocity due to the motion of the floating base, and JCCJ, that is the effect on the foot velocity due to the motion of the joints. So if I do like we have the robot here, we have a foot, so the velocity of this foot will have JCD x b omega e dot plus JCJ QJ dot. So QJ, let's say, are the joints, are all the joints, but because of the branch structure of the robot, JCQ is block diagonal. Okay, let's say now we are considering only one contact. So we have, and you considering one like the first one. So we'll have n column, but for example in the case of quadruped, only the first 3 columns will be different than 0, because the motion of the whole motion of the joints, the foot first foot is affected only by the joint of the leg it nods. So if you have the second foot here, we can have suppose then like this, that will have non-zero columns only in the correspondence of the second leg joints. So this is just to let you know how does it look like. While so think about this part. It's I'm moving the joints and the foot moves because of the motion of the joints. While this part here is I don't move the joints, I move the base, and I see a motion of the base of the foot because of the motion of the base. And how does it look like? So first we have, in essence, the motion of the foot. It's the linear motion of the base. So we have the base velocity here. Plus we have the linear motion of the foot. Let's say this is like we are talking about a point foot due to the rotation of the base. So you see here we have an omega cross the distance, omega base cross the foot position. The foot position from in the base frame. Okay? So if you write this in matrix form, it becomes whatever you see there, because you have the JCB equal to the foot position. Sorry, we are talking about the linear part here only, but you can have the angular part is just the identity. Plus omega cross xf, which we can write as xfb cross omega with a minus, and we can use the exclusive matrix operator to write this way. So we have xfb exclusive matrix operator. If you have also a flat foot and you have the angular part, then you will have the orientation of the foot, the motion of to the angular velocity of the base is affecting directly the angular velocity of the foot frame. And of course, this foot position in the base frame, if we are considering the word frame as reference frame, we need to compute the position of the foot in the word frame minus the position of the base to get the relative position. Everything is clear?
In this case, the Jacobian is expressed in the frame, in the base frame.
No, in this case we express in the so one thing is the.
So the words you are missing a rotation matrix from the word frame to the base frame.
Correct. Good point. Yeah, this is R.
No, that one I think it's
if this is in the word, yes, sorry, that's one. Yeah.
Yeah, on the rotation part, let's say.
Yeah. It depends omega b if you have in word.
Yeah.
Okay. So a remark is that all quantities should compressed in the same frame. And we can, if we look at the mass matrix, this can be partitioned in the following way. So we have first the dimension. As we said, it's square matrix, symmetric, positive definite of n plus 6 times n plus 6 elements. This is the what we call what for fixed base robot we call the joint space matrix, that is n times n, and we have the MB matrix, which is the matrix, the joint space matrix part affecting the floating base variables directly, and then we have also the coupling. So these are the coupling coming from the joints into the floating base part, the other activated part, and these are the coupling coming from the floating base part into the activated part. So think about a robot floating in the air that is moving his leg like this. It will have an effect on the base acceleration, and this is due to this term, while here this is the let me think how to express this. Yeah, let's say somebody push from outside. Let's say the trunk of the robot and the leg will the joint of the leg will go up. So this is the coupling to the joint variable. This effect is very important whenever you have a heavy leg. Think about IQ real instead of IQ that has the legs that are weighting 2 times, almost double with respect. I mean, to their influence, their inertia with respect to the trunk inertia is much. Their mass with respect to the trunk mass is much bigger. So the effect of this leg during the trot, for example, you see these legs are moving up and the trunk it's destabilized because of the motion of the leg. So if you want to do whole body control for IQ real, you really need to take care of this term. While with IQ that has very lightweight leg with respect to the trunk mass, you see that they don't affect. Okay. Then this is called the momentum matrix, sorry, of an articulated body, and this is the in essence you know that the momentum, the total momentum is equal to some inertia, let's say, times the velocities. So this is exactly what it represents. In this case, we have the momentum of the floating base, and the A matrix shows how it's related to the generalized velocities. So this is 6-dimensional. This is 6 times n plus 6, because in the generalized velocities we have the underactivated part and the joint part. Finally, is what we called MV. It's called the composite rigid body inertia, and in essence, you can see that as the inertia of the robot, as you you fix the joint variables in a certain configuration. So think you are soldering all the joints, and the robot it becomes from n plus 6 becomes a 6 degrees of freedom rigid body, a single rigid body that will have a mass that is the sum of all the masses of the links and the trunk, and the inertia, tensor of inertia, that would be the angular part of this Inv matrix. And it's called also spatial inertia if you use the generalized coordinate with the spatial velocity of the base as to represent the base velocity. And it's called also locked inertia. So the way the inertia the robot will have if we lock or fix all the joints. So as for the center of mass, let's say you do a weighted average of all the links. You need here to map all the spatial inertia of all the links into a common frame to compute that. So the properties of the matrix is as before, is symmetric and positive definite. The Coriolis vector now is a vector, so the bias vector that has a Coriolis vector, sorry, here it's missing the Q dot. And the gravity term, it's n+6 dimensional. In general, the Coriolis matrix is chosen such that this matrix is Q-symmetric. This is just a way of choosing that because we can have some properties that like this that we can use for proving stability, for example. Then the gravity vector is as follows. So it's the mass times the gravity. This is what we call the gravity itself vector 0, 0, 9.8. And this is the gravitational acceleration expressed in the inertial frame. So if we are writing this equation in the base frame, you need to put a rotation matrix here to map the work frame to the base frame. And then the kinetic energy, it's cool because you can write it either in the joint space or in the twist, using the twist of the links. So you sum up the spatial velocity times the spatial inertia, the product of the left and right product of the spatial velocity times the spatial inertia, and you sum up for the links, and you will see that is equal to the generalized velocity transpose times this mass times against the generalized velocity. Everything's clear? So now let me tell you about some important facts about the floating base dynamics that we kind of already discussed briefly. And the fact that the torques only affect the joint coordinates. So it means that we cannot have a direct influence on the motion of the floating base part unless the robot is getting in contact with the environment. So until we are in the air, we cannot do much. We will see that we can do something, but we cannot do much to control the position. Certainly we cannot control the position of the base, because the base will be falling under the effect of gravity with g acceleration. That's it. Okay? We can control the position of the base whenever the robot touches after falling the ground and some contact force appears. Then, if we neglect the inertial coupling here, this, the floating base, it can be controlled only through the action of these contact forces. But these contact forces have some limitations. there are some, we saw that in the contact model that the contact forces can be, no, we didn't see that, I don't remember. So there are some physical laws that are limiting the values that the contact forces can achieve, that are due to the fact that the leg can get a contact that is only unilateral, so the leg can only push but cannot pull from the ground. So the contact force should always be in this plane, and cannot be entering in the surface, because this would be a pulling force. So can only push, unilateral contact. Additionally, you can have also that the torques are limited because we have a limited actuator capacity. We cannot apply whatever torque we want. So we have torque limits. And this creates limitations on the ability of the robot to control displacement of the space. Okay? Then the last point is that the underactivated part of floating base coincides with the Newton-Euler equation of motion. We will see, I think, next lecture how this is how the floating base, how do the Newton-Euler equation looks like in detail. The Newton-Euler equation are linked with the variation of linear angular momentum of the whole system, of the system as a whole, as a rigid body, due to the effect of the contact forces. And they are obtained balancing these external forces and moments coming from the contacts and computing this rate of variation of linear angular momentum. When the last point is that whenever that we should underline is that whenever we supply a certain torque to the actuators and the robot is in contact, the environment reacts, producing a contact force, and this contact force acts on the underactuated dynamics and allows the robot to move in the environment. So the locomotion problem can be split into two consecutive stages. First, find the force trajectories that drive the underactuated dynamics in the desired direction we want to move, and this will result also in a centroidal trajectory, let's say a motion of the robot base. And then in a second step, compute the required joint torque, the profile of joint torques using the actuated dynamics in order to have the contact forces required under the hypothesis of non-sliding contact, because we remember that we cannot apply whatever force. So also the non-sliding contact should be, if we do an optimization here, for example, which people normally do, they also add the non-sliding, non-slipping constraints that are the friction points in this stage. And why we want to do that? Because this is a smaller problem. It's a 6 degrees of freedom system, and we can have less state variables. While here we have just the last step to go back to the floating base part. You have any question? So do you want to do a short track now, and then like 10 minutes, and then we see the last part. Okay, stop it.